Transistors, bipolar junction transistors, or BJTs. These are covered in Chapter 9 of the textbook. Of course, we're going to supplement the textbook. I've never had a textbook that teaches everything that I thought that needs to be taught. So there's things in the PowerPoint slides that we'll be going over. Of course, these PowerPoint slides are available to download as either one slide per page or 3 slides per page, which gives you a place where you can actually put notes about each individual slide. If you understand how a water valve works, then basically you should have little problems with understanding how a transistor works. But a basic water valve, we have a flow control, which we can actually control the actual flow of the water through the valve. We get a mechanical advantage it's an incline. It's actually a screw, but it's an incline that allows us to spread the force over distance, which means it takes less force to turn the handle than the force or the flow that we're actually controlling. So if you try to take your hand and stop the water flow, you're going to end up with mess, right? So if we can't control the flow of the water with just our hand covering the thing, but we can precisely control the flow of the water with the valve. So basically, transistors are electrically controlled current valves. So what we do with a transistor is we control the flow of current, but instead of doing it manually like we have to do with the water valve, we're going to do it electrically or electronically. We have 2 categories of transistors. The first chapter 9 covers the bipolar junction transistor, or what we call a BJT. This is going to use a small current on a lead that we call the base. The first thing we'll have to do is understand and get the nomenclature of this thing. But it's going to use a small base current to control a proportionally larger current between the 2 leads called the emitter and collector, and we'll look at that later. Then we have field effect transistors, or FETs. These use a small voltage applied to the gate to control a proportionally larger current between the 2 leads called drain and source. But this will be in the next chapter, FET. So these are the 2 types of transistors we have. We have a bipolar transistor, junction transistor, that uses a current to control a larger current. And then we use the FETs, use a voltage to control a proportionally larger. So the structure of a BJT is constructed of 3 doped semiconductor regions that produce 2 p-n junctions. The regions are named the emitter, the base, and the collector. So this is the name of the 3 regions. They have names that you need to, of course, learn. We have 2 types of BJTs. We have what we call an NPN transistor. These have 2 regions separated by a small p region. And then we have a PNP transistor, that bipolar junction transistor, a BJT. Then we have 2 p regions that are separated by small n regions. The NPN transistor is the most widely used, so we'll spend most of the time on that. Basically, the transistor works with 2 diodes with 2 p junctions. So basically, this is, of course, this is blown up. This is basically the way these things are constructed. So the one on the right, this would probably be the easiest to explain than the one on the left. So what we have here is this is an NPN. Notice, so we have 2 N regions that are separated by a P region. So we have an N and an N separated by a P. So this is an NPN transistor. Over here we have 2 P's separated by an N. So this is a PNP. We'll learn the basic difference between the 2. But like I said, we're going to spend the most time on the NPN because it's the most likely. So doping. we know doping can be introduced into the semiconductor lattice to control the conduction characteristics of the semiconductor. But what we have is we have the emitter. This guy is heavily doped, so it's got a lot of majority pairs. So if this is an NPN transistor, then there'd be a lot of free electrons moving around inside this thing. If it's PNP, then there'd be a lot of holes ready to move inside it. The base is lightly dosed. So if it's an NPN, of course, this means an NPN, then that's the P material, so it's going to have holes, but it's going to be few holes. Not as many electrons as it's going to be moving. And then the collector is moderately. So the p-n junction joining the base to the emitter region is called the base to emitter, and we'll abbreviate that BE. So anytime we see that in the data sheet, that means that's the junction that's between the base and the emitter. The junction joining the base and the collector regions is called the base collector junction, and it's abbreviated BC. So anytime we see BC in the data sheet, that's talking about the junction between the base and the collector. Anytime we see BE in the data sheet, this is talking about the base to emitter junction. Now, how we identify these things, these are the actual symbols of the two transistors. And what we look at first is we look at the arrow. The arrowhead always identifies the emitter. Now, if we look at one symbol, the arrow is pointing out. If you look at the other symbol, the arrow is pointing in. So the way we look at this, NPN is not pointing in. So this guy right here is not pointing in. So this is an NPN. And then pointing in, so this would be a PNP. And those are little tricks that we use to that. But the arrow always points toward the end. So if the arrow is pointing like this, then this has got to be the P. Right? You understand that? I'm sorry. This has got to be the N. So that means this would be a what? P and T. Here the old arrow is pointing out, so that means the arrow always points toward the end. So if that's N, this has to be the P, and this right here has to be. That makes sense? And those big symbols. Are we okay? In order for the transistor to operate properly, or to conduct, I shouldn't say property, I should say conduct. The two p-n junctions must be supplied with external DC voltages to set the operating conditions, and we know this is called bias. So DC voltages that are applied to a semiconductor to set its operating conditions, we call this bias. To make the current valve conduct, the base emitter junction has to be forward biased. The base collector junction has to be reverse biased. Since the base emitter is forward biased, even though the base collector is reverse biased, this conduction is still referred to as forward biased. So it's a little different on DSN diagram. So what we mean, if I come over here and this is an NPN, then let's right now, just for the heck of it, let's connect this to a common. And this is an NPN. Then I'm going to have to make the base positive in respect to the emitter. So if I'm going to reverse bias the collector, then the collector's got to be more positive than the base. And this is the way I teach. I don't teach that the cathode has to be negative and the anode has to be positive. I teach in respect to. So this would reverse bias it, because what we're going to do is we're going to look at this thing like this. So if you look at that like a diode, you can see that the cathode is more positive than the anode, so this guy is reverse biased. So we have to reverse bias the emitter. We have to forward bias the base to emitter junction. We have to reverse bias the base to collector junction. When this happens, then the transistor will conduct. Here's the main conduction path in the transistor. So this is the valve that we are actually controlling. This is the main conduction path right here. So we're controlling the size of that valve. Whether it's open, it's not true. We're controlling how open or closed that valve is. The size of a valve determines how much flow it's got to control. The remainder of this discussion will only deal with NPN transistors. The base, voltages, holes, and electron flow we reverse for PNP. So everything that we talk about on an NPN, we just reverse everything for a PNP. The forward bias from base to emitter narrows the base to emitter completely. The reverse bias from the base to collector widens the base to collector completely. The heavily doped N emitter region is packed with free electrons that easily distribute to the forward bias base to emitter. So this is showing a 2-battery. Later on, we'll learn how we can do this with, and I say battery. This is not the symbol of a battery. This is a symbol of a. So it could be a battery. So this is 2-battery bias, which we're going to do. So notice on this one, we're using common or ground common as emitters connected directly to common. So I have to make the base positive in respect to the emitter. So what we would do is notice the positive supply on this battery. So this is the base bias battery. The positive is pointing toward here. So I put the positive here in respect to the emitter. So that junction is going to be forward bias. Now we know this power supply right here, if it's plus 5 which we're going to have to do to be able to control it a little better, and later on we'll learn that we'll make this better. But if this is plus 5 when we forward bias the P-N junction, we would have a short circuit, right? So the purpose of this resistor right here, if this is 5 then we've got to put a resistor in there to drop 4.3 volts, right? This is silicon. Then notice over here we have this technically should be drawn maybe as one straight. This guy right here is going to be a lot higher, but this is 5 let's say this is 16 volts because we have to get 4 biases. So what happens is we come over here and we have this big plus and this little plus over here. So that that reverse bias is the collector is the base junction. Little plus, big plus, right? You understand that? And of course, this is to actually give us the ability to drop the voltage on the collector, and we'll look at that as we go on. Over here on the PNP, notice the batteries are reversed. So here we have the negative respect to common, so that's in respect to the this. This is going to be a lot bigger negative. So if this is plus 5 then this right here might, so if this is minus 5 this right here would be minus 15. And so what we're doing is we're making the collector more negative than the base. So that's reverse. Everybody okay? So in this thing we conduct, in the conduction path, if we're doing electron flow, would be this. And we're going to very seldom in transistors deal with electron flow. We're going to just say current flow. The base region is lightly doped and very narrow so that it has very limited number of holes. Only a small percentage of the electrons flowing through the base emitter junction can combine with holes in the base. This generates a very small base current. Most electrons flow from the emitter into the collector's depletion region because they are pulled through the reverse bias base to collector junction by the large positive collector supply. The electrons are pulled through the reverse bias base to collector junction to the collector power point, usually through a resistor somewhere in that path. The electrons move through the collector region, out through the collector lead, and to the external collector voltage supply. The amount of current, collector current, is controlled by the amount of base current. So base current is like the handle on your valve that you're controlling the size of the opening in your valve. So you get a lot of flow. You get a lot of water flow, or very precise control with very little effort on the valve handle. So this is what we're showing. So this would be I don't identify this guy yet, so it's an NPN. So over here I've got 16 volts building up here. Down here I've got 5 volts. So what happens is as soon as I do this, then this breaks down the depletion region once we exceed the drop. So for silicon, the emitter base is going to drop around 7/10 low. For germanium, it would be around 3/10. These are the two signatures. Now what I have up here is I have this big old positive voltage sitting right there. There's not enough holes inside the base to handle all the electrons that are flowing into the base. So what happens, these electrons get right here, and it's this big old positive base sitting right there. So what that's going to do, it's going to suck the majority of the electrons out of the collector base. And that's how this thing works. So we're going to have a very, very small base current that's going to control a very large collector to emitter current. And the more current I put into, the more current I put into the base, then the collector to emitter will increase by a proportional ratio. So what that means, if I double the base current, then the collector to emitter current, or the emitter to collector current, double. So what we're doing is we're controlling the flow. The main flow is between the emitter and the collector, the main flow. So we're going to use a small base current to control a proportionally large emitter current, emitter to collector. So I'm going to pause the recording because this is a copyrighted video, and I've already got trouble once too. So, but this video, there's a link to this video up on Blackboard. I might have to